All right, everybody, let's go ahead and get started. Before we get started on today's stuff in chapter 16, I've been looking at the inverted lectures, and I've noticed a common issue that has been coming up on the last question about taking benzene to ethyl propylbenzene that's meta to one another, right? What's the issue with this? What's the issue that we have to address? They are both activators and they're in the meta position. Why is that an issue? That's right. So each one of these groups is an ortho-para director, and yet we're putting them meta to one another. That seems to be a problem, right? So one of them is going to have to be a meta director, at least temporarily, right? What might that meta director be? Well, it might be a ketone. That's right. So we might put a ketone there and then figure out how to do the chemistry. Now I'm going to show you the correct answer first, and then I'll go over some of the things that I saw and why you need to pay attention to some of this. So the first thing that we need to do is install a meta director, and in this case we're going to use the Friedel-Crafts acylation reaction to do that. And I'm going to put in the first three carbons that I want. 1, 2, 3, right? So there I have a meta director, correct? Now what do I need to install? What do I need to install now? I need to put the other group in there. Now, how can I do that? I got to put 2 carbons in there. How can I do that? What reaction will I use? Pardon? Yeah, so we can use ethyl chloride, aluminum trichloride, and now we have the groups that we need. They are meta to one another, and now all I have to do is what? I have to remove the ketone by reduction. What reducing conditions will I use? You can use zinc and HCl, or zinc mercury amalgam and HCl. The Clemmensen reduction will work just fine here, or the Wolff-Kishner. I counted both of those. Okay? Another way that you could have done this is you could have done a second Friedel-Crafts acylation, put another ketone there and reduced. I would have counted that. Okay? I would give you full credit for this. Many of you started off by putting in the ethyl group and then putting in the ketone. That would go para, right? Because that ethyl group, being an alkyl group, is simply a ortho-para directing group. Okay? Brian. You can in theory, but that's got a problem, and that's the one. So let's assume you do that. And so you put in the 2 carbons that you need, and you're thinking, well, I'll just reduce that at some point, right? That won't work. Why? Because if we did that, we would end up with that product. Why would we end up with that product? Carbocation rearrangement. That's right. Remember, the aluminum trichloride will essentially remove the chlorine and give us a cation that will quickly rearrange into a secondary carbocation. This was the one that most people attempted and got wrong because you forgot that you're going to generate a carbocation intermediate which will rearrange. Okay? So you got to pay attention to those details. So 2 issues were, one, starting with the ortho-para director and then putting the next group meta, okay, or following this route and getting the rearrangement. Now, if you had done this, followed by bad acid chloride and then reduced both of them, that would have been fine. I would have given you credit for that. But you got to pay attention to what kind of groups you're putting on and what order matters. If you put the orthopara director on first, it's going to direct the next one orthopara. Just because it's a ketone doesn't mean it's going to go to the meta position, right? It depends on what substituent's already on benzene. So I haven't completed all the grading yet, but I wrote on many of them, see me about this, and so I thought that's a lot of people that are going to come see me, so we're addressing it now. Okay. So you're still more than welcome to come see me, but hopefully that'll address some of those issues. Okay. All right, today we're going to continue on in chapter 16. We talked about last time the fact that we can take esters and reduce them directly to aldehydes using a reagent known as diisobutyl aluminum hydride, known as dibal or dibal, depending on your pronunciation. Okay, I pronounce it dibal, but whatever, tomato, tomato. Okay, this reaction on paper works very, very well. In practice, however, it's a little more finicky. Can anybody explain to me why it might be a little more finicky in practice? What do you know about the reactivity of aldehydes with respect to esters? More reactive or less reactive? They are more reactive. Esters are less reactive. So you're taking a less reactive starting material and making a more reactive product. That's always tricky. Okay? It is possible to do if you are very, very careful with the equivalence of diisobutyl aluminum hydride. So you need to know the concentration of your solution of that very, very accurately. And you need to add it slowly at very, very cold temperatures. Okay? And you can get it to go. But it is a finicky reaction. Okay? I've tried to do this reaction numerous times, and I think the only time I got it to work well maybe was a time or two. Okay? It's just, you've got to pay very close attention to all your details. It has to remain cold. You have to know exactly how much diisobutyl aluminum hydride you have. You have to add it very slowly over a long period of time, which makes maintaining the temperature a little difficult. And what you'll notice is that, of course, dibal is neutral. It has only one hydrogen and two isobutyl groups. So this has a vacant p orbital. It's a Lewis acid. When you add this slowly into the mixture of ester, it forms a Lewis acid-Lewis base complex, where the ester carbonyl oxygen is functioning as a base, and you form this intermediate. Now that you have the aluminum in the formal negative charge, just like lithium aluminum hydride, now that you could think of this as a hydride donor. This is really close in proximity to the carbonyl. And so it can transfer that hydrogen, break that weak pi bond, and it stops there until you work it up. And then when you work it up, it decomposes into the aldehyde. However, if you warm it up a little bit, it will actually decompose into the aldehyde in the presence of more diisobutyl aluminum hydride, which means it gets reduced to the alcohol. So it's a very finicky reaction. It's one of these reactions that we like to write on paper, but in practice actually turns out to be a little more difficult. So we only try to do it when it's really the only reaction for us, okay? So what happens, like I said, you form the Lewis acid-Lewis base complex at low temperature. That hydride then transfers, and you end up with this type of intermediate, which then can lose the alkoxide as a leaving group, and you end up with the aldehyde at low temperature. And since this step is actually fairly slow, so all of your diisobutyl aluminum hydride has been consumed. This is fairly stable at that point because you don't have any more reducing agent around, and then when you add water, you cleave the oxygen aluminum bond and you get the aldehyde, okay? So again, a very finicky reaction, but on paper it does work. Actually it does work, but it requires a lot of finesse. So there are other ways to get to aldehydes. So let's suppose you have an ester that you wish to convert into an aldehyde. However, the only reducing agent you have in the lab is lithium aluminum hydride. Tell me how you can perform this transformation. You have all the tools in your magical toolbox at this point to do this transformation. Okay, so Rose wants to do that transformation. She goes in and looks to see if I have diisobutyl aluminum hydride, and she finds that all I have is a really, really old bottle that looks yucky, and she's concerned about using that, so she says, no, we're not going to do that. We're going to find another way to do this particular transformation. How is she going to do it? What do you think, Blaine? That's a new excuse. You're allergic to questions? That's okay. What do you think? The only thing she has is lithium aluminum hydride. So what's going to happen if we take an ester and react it with lithium aluminum hydride? What are we going to get? We're not going to get a carboxylic acid. What do you think, Harrison? What's an ester going to give us if we take it and react it with lithium aluminum hydride? It will be an alcohol. That's exactly right. What kind of alcohol? We're going to end up with we're going to end up with two primary alcohols, actually, right? You're going to end up with the alcohol here, which would be methanol, which we're not concerned with because it's not included in our product. And you'll end up with the primary alcohol here, right? So now what do we do? So yeah, we can reduce it all the way to the primary alcohol. We can't stop it at the aldehyde with lithium aluminum hydride, right? So now what do we do? Blaine now has her primary alcohol in hand. What does she do?
Why don't you reduce it to an alcohol, then go back and make it an aldehyde?
Tell me how. What do we need to do? You're right. Oxidize it with what? PCC. That's exactly right. Most of the time when you read a real research paper where they're taking an ester into an aldehyde, most of the time they don't attempt to do dibol reduction. They will reduce it all the way to the primary alcohol, isolate that primary alcohol, and then oxidize it with something like PCC. There are other reagents today that we can use, like the Swern oxidation, okay, which will also do the same transformation in terms of oxidizing a primary alcohol to an aldehyde. But that's usually the way that they go about it. It's a two-step process where you're reducing all the way to the alcohol and oxidizing back up to the aldehyde. Yes, it's an extra step, but both of those steps aren't very finicky. The only thing you have to be concerned about with the lithium aluminum hydride is that the reaction is dry. That's easy to do. And that you have access to PCC, which not hard to do, right? Both of those reactions are so well behaved that, you know, any one of you could come into the lab and get that reaction to work and isolate the product and move on. If we were to actually have you do the dibol reaction, maybe 2 of you out of the class would actually get a yield of aldehyde. Pretty confident there, aren't you, Matthew? You'd be one of the 2? Okay. So there's more than one way to get to your final product, right? You're starting to have a lot of tools that you need to manipulate. Okay. Some of the other carbonyl, quote unquote, containing functional groups, right? Like nitriles, although there's not a carbonyl, they still are in the same family because of the oxidation state of the carbon. You can reduce the nitrile to the primary mean using lithium aluminum hydride. We're adding 2 equivalents of hydrogen across the pi bonds. Lithium aluminum hydride is that source of hydrogen. Where do the hydride hydrogens go, on the carbon or the nitrogen? What do you think based on the mechanism? If we think of lithium aluminum hydride as H minus, where will that H minus attack? The carbon of the nitrile or the nitrogen? It would be the carbon. Now tell me why. Okay, very good. Yeah, so it's more electropositive. What else? Nitrogen also has a lone pair, right? So if you're something that's negatively charged, you want to go to some place that has a lone pair? No, right? You're going to want to go to some place that's more positively charged, right? And so the hydrogens on the nitrogen actually come from the aqueous workup, okay? We can also take nitriles and reduce them directly to aldehydes with dibol, at least in theory, right? That's the general reaction. What's strange about that reaction? Where did the nitrogen go? And where did the what come from? Where did the oxygen come from? All right. Where do you think the oxygen came from? Water. That's exactly right. The oxygen comes from the water, and we'll talk about the mechanism of that here in just a moment. Okay? So, let's just go ahead and start talking about that right now. So we have a nitrile. I'm just going to use this one. And we're going to end up with benzaldehyde through this process. And again, we can think of dibal as a H minus donor, as a single equivalent hydride donor. So where's that hydride going to go, Matt? It's going to go to the carbon, right? The hydride's going to attack the carbon. We're going to break one of the weak pi bonds. We're going to end up, there's the hydrogen from the hydride. There's the carbon of the nitrile. And I end up with that. And that's all that happens at that stage. Now what happens? We dump it over water, right? So Brian, what's going to happen when I dump this over water? Is this a strong base or a weak base? Relatively speaking. N minus. It's fairly strong. Water is a relatively strong acid in that case, right? So what's going to happen? We're going to protonate. And we're going to end up with what's called an imine functional group. Which are useful in and of themselves. We'll talk more about those later. And since we dumped it over excess water, we got lots of water. And we set up that equilibrium. Anybody want to show me the step-by-step mechanism for how that nitrogen gets replaced with an oxygen? Gabby's shaking her head no. She doesn't want to show us that. What do you think's happening? Okay, very good. How? Got lone pairs, right? It's going to attack what? Attack the nitrogen. If it attacks the nitrogen, you'd be suggesting I'm making an oxygen-nitrogen bond. Do I see any of that? Okay, so we have this going to the carbon. This is all reversible, actually. What do you think happens now? What kind of base is this, strong or weak? What do you think, Jamie? Think that's a fairly strong base or a fairly weak base? N minus? Fairly strong. What about this? O3, or let's see if we think of this like H3O plus, be strong. So I've got kind of a strong base and a strong acid. Are they going to coexist together? No, not at all, right? And so the base will react with the acid. We end up there, right? See where we're going? Now what has to happen? This gets protonated because we're losing ammonia, right? Usually when we dump it over water, we also dump it over a dilute acid, so there's a little bit of acid around. So we get this. We get our ammonia, which is a gas. Which then gives us this, which then loses a proton to the water, right? So the acid is actually catalytic, and you end up forming the aldehyde. A lot of steps, right? It's a lot of steps. It's Le Chatelier's principle. It's Lewis acids and Lewis bases. Lewis acid, Lewis base. Lewis base, Lewis acid. Lewis base, Lewis acid. Lewis acid. It's nothing more than a series of Lewis acid, Lewis base reactions. But anytime you have a carbon-nitrogen double bond, like an imine, that can be exchanged out for oxygen through this process. Okay? And it turns out it's very important for your eyesight that this happens. Okay? We'll talk about an example of that later on, probably on Wednesday. I don't know if it's in the slides for today or not. But this is how your eyes regenerate the connection between the opsin and all this other stuff is by this reversible process through an imine linkage. So you have an imine that detects a photon, sends a signal to the brain. After that, it's dead, and it has to be regenerated. Well, since it's an imine, that can be converted back to an aldehyde, and then another amine can come in and form an imine, and that's how that gets recycled. We've already talked about ketone synthesis with oxidation of secondary alcohols, Friedel-Crafts acylation reactions. Don't forget ozonolysis of alkenes is also another way to make ketones, right? So we can make ketones by a variety of reasons. And now you have another way of making them, right? In terms of nitrile chemistry, right? So if we take a nitrile and instead of using a hydride nucleophile, we use a carbon nucleophile, I'm going to get a ketone, right? When we use the hydride nucleophile, we got a aldehyde, okay? But now I can use a Grignard or an alkyl lithium, right, which can function as a nucleophile and attack the carbon of the nitrile, break that weak pi bond, and then after water workup, we'll exchange out that carbon-nitrogen double bond for a carbon-oxygen double bond, and so we can get a ketone, okay? You need to be building roadmaps for how you make ketones, how you make alcohols. You need to know how these things are interrelated and connected, okay? And so again, the mechanism is quite simple. You end up with an imine that ultimately gets hydrolyzed to the ketone, okay, through hydrolysis. And that equilibrium is shifted to the right in that case because you dump it onto a huge excess of water with a little bit of acid, right? So there you go. So here's some examples of how we might conduct this reaction. Butane nitrile plus phenylmagnesium bromide can give us this aromatic ketone. Okay. That's one way to get to that ketone. Another way to get to the ketone would be to start off with the benzonitrile and then use an alkyl lithium or an alkyl Grignard. I can get to the same ketone. What would be the third way that you know how to get to that ketone directly? Pardon? Friedel-Crafts acylation, that's right. So if we had benzene, right, and then this acid chloride, where this is a chlorine here, mix them together with aluminum trichloride, we could get there. How else can we make that ketone? If we had the secondary alcohol, we could oxidize it, right? So there are many, many ways to get to that simple ketone using a variety of reactions that you already know. Okay, so which way would be your preferred way to make it of all the ways that you know? If you could have any starting material you wanted, what do you think your preferred way of making it would be? Just name one. Grignards are real easy to work with, so that top reaction might be a good way to do it, right? Okay. Grignards are pretty easy to work with. They are a little water sensitive, right? So you got to be careful about how you work with them. You all do the Grignard reaction this week? Is that this week? Maybe. Snapdragon? The Fischer esterification? Okay. Another thing that we can do with carbonyl-containing compounds like ketones and aldehydes is we can add water across the carbon-oxygen double bond. What would that be very similar to? What else have we added water across? An alkene. And when we added water across an alkene, we got a alcohol, Markovnikov or anti-Markovnikov? Ah, very good. It depends on the conditions, right? So if we just used water and acid, it's a Markovnikov alcohol. If we do hydroboration oxidation, it's a anti-Markovnikov alcohol. But here, you're going to add the OH to the carbon of the carbonyl, and you're going to add the hydrogen to the oxygen of the carbonyl, okay? And these are known as hydrates, okay? It is a hydrate. So when you take a aldehyde or a ketone and you place it in water, it is in equilibrium with its hydrate. Where might you suspect the equilibrium to lie, to the left or to the right, just on what you know right now? What do you think, Katie? Would you expect the equilibrium to lie to the left or to the right? On what you know about bonds and stability and all that kind of stuff. You might expect it to lie to the right because of what? All sigma bonds, that's right. And they're stronger than pi bonds, right? So she would be sacrificing a weak pi bond and gaining strong sigma bond, right? That's true, okay? So that sounds like the equilibrium should lie to the right. And in some cases it does. It depends on the electronic structure of the ketone or the aldehyde. Okay, aldehydes typically lie more to the right than ketones do. Ketones typically favor the carbonyl, okay? Because ketones have those two electron donating groups that stabilize the ketone, okay? Whereas aldehydes only have one. And so the equilibrium doesn't have to lie to the right in all cases. That's what we're talking about. This is a gem-diol, meaning geminal, okay? The OHs are shared on the same carbon. So we go from an sp2 hybridized carbon to a sp3. Very good. Okay? Now, if we look at the equilibrium constants, or at least the apparent equilibrium constants, okay, K prime, which is the equilibrium constant times the concentration of water, okay? Why can we do that? Because the concentration of water really isn't changing much. So we can do this and call it an apparent equilibrium constant. What you'll notice is formaldehyde has a equilibrium constant that's small or large? Fairly large, right? 2,000, right? So it lies clearly to the right, just as Katie predicted. Okay? However, acetaldehyde, what do you think there? Where does the equilibrium lie? Does it lie to the left? Slightly to the right, right? It's only 1.3, right? So it lies slightly to the right. Okay? Acetone, your fingernail polish remover, when you rinse it off in water, where does the equilibrium lie? To the left, way to the left, actually. There's very little hydrate. Okay? And so what we can say from this, right, is that ketones typically favor the ketone form. Aldehydes will either slightly favor or favor the hydrate form. Okay? But notice what happens when we put big bulky groups out here for the aldehyde. What do we see? It slightly favors the starting material, right? Why is that? Everybody's favorite answer. Steric hindrance. There you go. You put a big bulky group there, you're going to sterically hinder it, right? But notice down there for trichloroacetaldehyde, notice where the electron or where the equilibrium lies. To the right or to the left? Way to the right, way to the product side. So that tells us that if we have things that can withdraw electrons from the carbonyl, that's going to favor the product. Okay, so electron donating groups like we have in ketones will favor the starting material. Big bulky groups will favor the starting material. Small groups will slightly favor the product, and electron withdrawing groups will favor the product. Do I expect you to know those exact values? Absolutely not. I expect you to understand the trend, okay, of where the hydrate lies in terms of equilibrium, okay? You just really need to know that aldehydes typically favor the products and ketones typically favor the reactants. That's the big take-home message, okay? So, for example, for those of you who are in biology and have ever dissected a frog or a worm, how many people have done that? You pull them out of a solution of something. It does smell bad, right? It's embalming fluid, basically, right? It preserves tissue, which is a lot of formaldehyde. The thing is, though, is if you read the bottle, it doesn't actually say formaldehyde. It says formalin, which is a mixture of formaldehyde in water. And when formaldehyde gets placed into water, 99.9% of it is the hydrate. Formaldehyde is actually a gas. But when you bubble it through water, it forms the hydrate, the gym-diol. But that's in equilibrium with a small amount of the formaldehyde. And it's the formaldehyde that preserves the tissue. Okay? But it's not that you have it in a complete solution of formaldehyde. It's in a mixture of formaldehyde and water, which makes formalin, which is the hydrate. And almost all of it is as the gym-diol. If you take acetaldehyde, you're going to have 58% of it as the diol, right? The remaining part's going to be acetaldehyde. And if you take acetone, very little of it's going to be as the gym-diol. Most of it's going to remain as the acetone. That follows the trend that we learned before, okay? This is the reason why we can't oxidize a primary alcohol to an aldehyde with Jones reagent. Explain that observation to me. Why is that true, Sarah? What does Jones reagent have in it? Jones reagent is a mixture of chromium trioxide, sulfuric acid, and what do we dissolve sulfuric acid in? It's water. So once you form the aldehyde in a Jones oxidation, What does that aldehyde do? It reacts with water and forms the hydrate, which looks like an alcohol, and Jones oxidizes it again. So it will remove one of these hydrogens from the carbon. Well, there's only one. And it will remove one of these hydrogens from one of these OHs and make a carbonyl. And when we do that, that's a carboxylic acid. That's why I told you if you do PCC chemistry and you accidentally add water, it'll do the same thing because it forms an aldehyde. The aldehyde reacts with the water to form the hydrate, and the hydrate can then get oxidized again to the carboxylic acid. Okay, so it's that intermediate, that chemistry that happens with the aldehyde that's responsible for it. Now, if we use PCC and then dichloromethane, how much water's around? 0. So once we form the aldehyde, what happens? It stops. If you have excess PCC and you come in and throw water in, it'll form the hydrate, and that hydrate will get oxidized to the carboxylic acid. Okay? So PCC is selective only because it's soluble in dichloromethane, and dichloromethane contains essentially no water. So that's how you stop the reaction from going all the way to the carboxylic acid. Okay? Because you should have had that question because the oxidation state of chromium in both PCC and Jones reagent is identical. It should have done just the same chemistry that Jones does. Okay? But it doesn't because there's no water around. You had to have the water around for that next reaction. Okay? All right, let's talk about the mechanism. Let's take benzaldehyde. Of course, the equilibrium lies back that way, we know. But we can still detect this quite a bit. Tell me how this happens. One of the easiest mechanisms in the world. How does it happen, Nate? Think that's a strong enough base to pull off a hydrogen from water? Break a weak pi bond, right? We're not going to break a weak sigma bond. Now what happens? What do you think happens, Karina? We do what's known as a proton transfer. We got a strong base, strong acid, the proton's going to transfer, and we end up at the product. And of course, this is all reversible. Okay? So if I want to make the starting material go to the product, since it's a reversible reaction, what do I need? Whose principle do I need to use? LIAH liaison. What's the easiest way to make all of my starting material become product? Add a lot of water, right? Well, I could take something out, but that would mean distilling this. And this probably has a higher boiling point than the starting material. Technically, you're correct. But it would be practically difficult because alcohols, as we know, have higher boiling points than aldehydes because they can hydrogen bond, right? So distilling this out would be difficult over this. We'd actually end up distilling this out because it would boil at the lower temperature and it would drive the equilibrium the other way. So we'd have to be careful with that. But technically, right, we could remove something. But here, the easiest thing is just take the cheapest material you got, which is water, dump a ton of it in here, and that will shift it to the right. If I want to go from here to here, I could distill out the aldehyde or distill out the water or something like that, right? I can shift the equilibrium either to the left or to the right using Le Chatelier's principle. Okay. Now, being the good students that you all are, you know that alcohols are nothing more than organic derivatives of water. So if we can add water across a carbon-oxygen double bond and get a hydrate, we should be able to add alcohols across a carbon-oxygen double bond and get what are known as acetals. Okay? So we can take an aldehyde or a ketone, two equivalents of an alcohol and an acid catalyst, and we can make an acetal. This is a very useful reaction. Okay? Which way do you think the equilibrium lies, Mason? And why? New sigma bonds. That's exactly right. You might predict that. Okay? These are reversible reactions. And again, the equilibrium depends on the nature of the ketone or the aldehyde. Aldehydes typically favor the product. Ketones typically favor the reactants. But we can add a huge excess of the alcohol and actually force it to go to completion. Okay? There's also some other tricks that we can play in terms of things like making rings and other things that help stabilize it. One of the common acids for this reaction, TSOH. What is that? Refresh my memory. What's TSOH? Tossic acid. That's right, tossic acid. It is essentially organic sulfuric acid. Okay? And it's a pretty strong acid. You can also use sulfuric acid for this, but tossic acid is one of the common ones that is used. And so in this case, you can take the propanal, methanol, at least two equivalents. Usually we use the alcohol as the solvent, actually, so you have more than two equivalents around. Add a little bit of para-toluene sulfonic acid, and you get what's known as the acetal. Okay? Acetals are going to be very, very important for you when you get to biochemistry because sugars are acetals. And the chemistry of the acetal functional group is very, very important. Okay? It's what makes a reducing sugar and a non-reducing sugar a non-reducing sugar, is the nature of the acetal bond. Okay? So these are not ethers. It looks like two ethers sharing the same carbon, right? It's an acetal. It's a new functional group for you all to know. Okay? Now, it turns out that this is a pretty interesting reaction because it's very selective for aldehydes and ketones, but you can't form acetals from esters. And let's suppose that Karina comes in and she has this, what we're going to call a keto esters, because it's a molecule that has an ester functional group and a ketone functional group, right? And what she wants to do is just reduce the ester all the way to the primary alcohol. What reagent does she have in her arsenal that can reduce esters to alcohols? Lithium aluminum hydride, LAH, that's right. However, what's the problem with lithium aluminum hydride in this setting? It'll reduce everything. It's also going to reduce the ketone. That's a problem, right? She wants that keto alcohol, 6-hydroxy-2-hexanone. But she can't just take this and throw it into lithium aluminum hydride, okay? So, what is she going to do? She's going to protect the ketone, do the chemistry that she wants, and then get the ketone back, okay? So what she's going to do is she's going to take her starting material. She's going to use two equivalents of an alcohol. In this case, however, the alcohols happen to be in the same molecule. That's convenient. What's this molecule called? OHCH2CH2OH. It is a diol. You could call it 1,2-ethane-diol. You all know it as ethylene glycol, otherwise known as antifreeze, right? And so Karina takes this molecule, she takes the ethylene glycol, paratoluene sulfonic acid, and she heats it to reflux, and she gets the acetal. You can see that's a ring, a 5-membered ring that's getting kind of cut off up there. So she took the ketone, which is reactive because it has a pi bond, right, and converted it into a carbon that has the same oxidation state because it still has the same number of bonds to oxygen, right? But now they're all sigma bonds. Are they reactive towards lithium aluminum hydride? No. But the ester is going to be reactive, right? So now she treats this product with lithium aluminum hydride, works the reaction up and gets the alcohol that she wants. And now all she has to do is remove her protecting group. And acetals are easy to convert back into the alcohol by simply dumping them onto an excess of water and a trace amount of acid. You remove the alcohol, if you will, from the acetal very easily by the reverse chemistry, okay? So you've all learned a couple of protecting groups. Acetal formation can protect an aldehyde or a ketone. What other protecting groups have you learned so far this semester? Tosyl chloride wasn't a protecting group. It made it reactive, right? Trityl. And what were we protecting? Yeah, that's right. We were protecting alcohols as ethers, right? And so trityl was one example of that. The silyl and the tert-butyl ether, yeah. So now we've learned several protecting groups. You know how to protect alcohols. Why might you want to protect an alcohol? Because they react with things like organometallic reagents, right? Why do you want to protect a carbonyl? Because they react with things like organometallic reagents, and they react with hydride reagents. And so if you don't want them to react, you have to protect them, okay? Protecting group chemistry is the bane of the organic chemist. Why is that? It complicates things. Very good. What else? It's inherently wasteful. Why is it inherently wasteful? My protecting group's not ending up in my product, right? I'm using it temporarily and then I'm removing it, so it's wasteful. That's where biology beats chemistry every day. Biology has figured out through enzyme chemistry how to do these complicated things within an active site of an enzyme without having to put protecting groups on and taking protecting groups off. And that's what most of us are studying these days. How can we mimic what nature does so well in a test tube or in a reaction flask, okay, or in a little petri dish? That's what we're trying to figure out how to do every day, because nature's figured out how to make reactors that can do all this without doing the protecting group chemistry, okay? And so we're always trying to learn from Mother Nature.